Hi everybody, this is Rick, and welcome to our virtual Psych 301 lab, where we're going to be talking about and running through our lab script referring to conducting Factorial Anova and visually interpreting interactions that you would find from Factorial Anova. Notice that I posted a review of one-way Anova yesterday. I know the link was not working for some people, so I just went ahead and uploaded it to YouTube and reposted that link. So check that out if you need to. In keeping with that, we're not going to be doing any type of conceptual review of Factorial Anova. This is more of just kind of practical purposes type of lab. But this is something you will come across quite frequently in the literature if you haven't already, and especially the interpreting interactions visually is pretty relevant because these are pretty common to see in research articles whenever people do run these Factorial Anovas. So being able to interpret them visually and interpret them quickly is a useful skill to have in just being a good consumer of psychological research specifically, or just social science research broadly. So let's go ahead and dive in. Before we do, I guess I'll just quickly note that like the Anova review I posted, this is my first time using screen capture software, and I've never had to actually record a lecture like this before. So if it's a bit choppy, or if it's a little bit, just of a messy presentation, please forgive me. I'm still kind of learning the ropes of all this stuff, and like you, having to deal with the sudden change in workflow and change in just the methods by which I can conduct myself as an instructor, as a grad student, and all of that. So bear with me, and let's just go ahead and get started. So you should open up the lab script here, and you'll notice that I have a number of packages already put in here. You might have to actually install a few of these. I'm not sure, but I'm leaning towards thinking we've not used the PSYC package before in our labs, and we've definitely not used PSYplot before in our labs. The PSYC package we're going to use because it has these two functions, skew and kurtosi, not kurtosis, but kurtosi, and they give us estimates of skewness and kurtosis that are already normalized or transformed into Z values. Now this is really cool. I know in lecture from last Thursday, Dr. Siegel showed you how to make your own functions that uses the moments package, skewness and kurtosis functions within them. And within those custom functions, you get an estimate for skewness and kurtosis and transform them to Z by yourself. Here, I'm just going to rely on the functions that I already know work from PSYC package, and that might save us just a bit of complication in trying to create our own here. So this will give us skewness and kurtosis values that are already Z transformed. We're also going to be using the PSYplot package. Now this is pretty unnecessary for the broad picture of things, but because Dr. Siegel uses this PSYplot package in his presentation of Factorial Anova, I've just included it here, and it'll come up at the very end of part 1 of the lab script. So go ahead and install both of those things if you need to. If not, we can go ahead and get started. So we're going to get started by just reading in the data here. I know you guys should know how to import data by now, so I've just included this here. The data should be health factorial, and as always, it should be in the same folder as your R Markdown file, and it should be in that folder before you open your R Markdown file. And I also have just two vectors here for factors. I'm not even transforming these into factors, but these are going to be used in part 2 when we look at interpreting interactions visually. So I'm just going to go ahead and load in my data here, and I'll just quickly walk you through what this data is. So this data is completely made up and simulated by me, and it's kind of an extension of the data that we used last week. Now it's not the same data as last week, it's completely different, but it's just a few variables here that we need to go over. So I have an exercise variable, a diet variable, and the weight variable. The diet and the weight variable are things that we used in the one-way Anova lab script. These are things basically, in that analysis, we essentially just said, hey, we have these 3 dietary lifestyles of a no restriction diet, or no res, a vegan diet or a vegetarian diet, which I've just called veggie. And we have data for individuals' weights who adhere to these diets. And we ran an ANOVA to see if one diet resulted in significantly different weight than another diet, by which we found that the no-res diet was significantly, the people in the no-res group were significantly higher weight than those in the veggie or the vegan group. I've also added a variable for this particular lab script, which is exercise. So we're going to have some people in the no restriction group that do exercise and some that don't. We're going to have some people in the vegan group that do exercise and others that don't. And we're going to have some people in the vegetarian group that exercise and some that don't. And we're going to include this second independent variable of exercise in our Factorial Anova. I'll remind you that what we mean by a one-way ANOVA or a Factorial ANOVA is a reference to the number of independent variables that we have. So when we say that we're running a one-way ANOVA, it implies that there's only one independent variable that we're interested in. Here, when we run a Factorial ANOVA, it means we have more than one independent variable that we're interested in. So I'll go ahead and just read the background for our Part 1 Factorial Anova section here. And that is, with the knowledge that a no-res diet, on average, leads to significantly more weight than a vegan or veggie diet, researchers are now interested in how exercise might also influence weight. As their hired data analyst, you decide the best way to test this scenario would be to run a Factorial Anova to test whether there is a significant interaction between the two independent variables, exercise and diet. Because there are now two IVs, this analysis will be a two-way ANOVA, and more specifically, we can characterize this as a 3x2 ANOVA, or 2x3, depending on which variable you describe first. And those two numbers, that 3x2, reference how many levels of each independent variable they are. So we don't have independent variables in this ANOVA context that are continuous in any way. They're discrete variables, and they're categorical in that sense. So they have levels to them. So here we have diet, which we have those three levels of no-res, vegan, and veggie. And then we also have our exercise variable of do they or do they not exercise. So 3x2 Factorial Anova would be kind of the full way to talk about that. First here, we want to convert exercise and diet into factors. And if we go back and look at our data, we'll notice that both of these things are not given numerically. They're just given in terms of their kind of label already. And if I look here, I can see that they're character vectors as well. So what I'm going to go ahead and do is just use as factor for this, because I really don't need to specify the levels if I don't want to. And it just so happens that no-res, vegan, and veggie are also the alphabetical order, are also already in alphabetical order. So it's going to be nice and continuous from what we saw in the one-way ANOVA exercise last week. So I don't really have to worry about relabeling them to put them in a particular order if I don't want to. Although really, because this is not a longitudinal or time series type of data set, the order really doesn't matter in the first place. At any rate, I'm going to take dat exercise and convert that to be as factor dat exercise. And likewise, I'll take dat diet as dot factor dat diet. So I'll run these two things. You'll notice here in my environment, these should change to factors. There they go. I have diet with 3 factor levels, no res, vegan, and veggie, and exercise with 2 factor levels, no and yes. Next, we want to examine the crosstabs for these two things to see their sample size. And you can reference the last ANOVA lab script 2, where I've done this in a couple of different ways. I'm going to just take the easiest way and use my table function. If you remember from way back in the beginning of our tutorials when we talked about table just gives us a frequency plot. In other words, it tells us how many people belong to whatever variable we give it. So if I say, for example, dat exercise. It'll tell me that there's 90 people who do exercise and 90 people that don't. And the way the table works, we did this with Gapminder way back when, is that as I add more variables, it starts to cross-tabulate those frequencies. So if I add diet here, it's going to tell me not only how many people exercised in each category, yes or no, but it's going to tell me how many people, yes or no, exercised within each level of diet. In other words, it's going to produce a crosstabs table. So if I run this, because this is nice, clean, simulated data, you'll notice that there's 30 people in each group. So I've tried to make this like pretty legit for us in that way. Next, we're asked to examine the descriptive statistics for each cell. You can do this in a number of ways as well. I really like the tidyverse way of using summarize because it gives you a nice table that you can then save and reference later. Or when you start to kind of learn how to make more sophisticated reports, you can present this in your report as just the object that you save the summarize function as. So I'm going to start with dat. I'm going to add a pipe, and then I'm going to use summarize. And then now, if you remember the way summarize works, well, actually, excuse me. We're going to go dat group by, and then I'm going to tell it to group by diet and then exercise. So what that is going to tell R, and I'm also going to add another pipe there. What that is going to tell R is that everything that follows this group by function in this pipeline, I want to not only calculate that specifically for each level of diet, but I want to calculate that specifically for each level of exercise in each level of diet. In other words, like we have our crosstabs over here, it's going to calculate the mean, the variance, whatever I tell it to for the no res no group, for the no res yes group, for the vegan no group, and so on. So it's going to give me a very quick way of distinguishing between those subgroups without me having to do any crazy type of referencing or subsetting data or filtering only the 30 people who have no res diet and yes to exercise or anything like that. It's a very straightforward and streamlined way of doing things. And now I just get to decide, what I want to put in my summarize function. So here I'm just going to do some of the typical stuff. If you don't mind, I'm just going to go ahead and copy and paste what I have in the key here. So I'm going to summarize, and what I'm going to summarize is going to be the following. So I have here the mean, variance, standard deviation, min and max, and kurtosis and skewness. And notice this is where those two PSYC package functions are coming from, kurtosi and skew right there. I'll also note, because I've been asked this by some students in emails and such, why I'm putting this dot comma here. Now, when you use piping, as we learned, the pipe means and then. So if I start with my data set and add a pipe, it means take that data and then group by diet and exercise and then summarize function. And in a lot of cases, you don't actually need that dot comma, but tidyverse knows that if I put this dot comma here, that this dot is a stand-in for whatever came before. So here this dot refers to dat, and here in summarize this dot refers to group by and dat. Whether you really need it or not, it kind of depends. I just find that I got in the habit of putting it there, and so that's what I continue to do. Anyways, so I can evaluate these statistics here and get a really clean, nice table, or it's actually a tibble, that has all of my breakdowns per each group here. My means, my variances, standard deviations, all of that. So it's pretty cool. I'm going to go ahead and save this as an object called Factorial Stats. And so if I save that as an object, I'll just go ahead and copy and paste this name and reprint it. If I run this chunk all as one, there it is, Factorial Stats. And it's something that I can reference at a later time too, or look at separately from everything else I've done. So next, I'm asked to check the normality and homogeneity assumptions of this test. And there's a few different ways we could do this. And again, these are things that we saw when we looked at our one-way ANOVA lab script, or when hopefully you looked at it from last week. So we can look at normality in either a numerically driven way or a graphically driven way. I would suggest always doing both. So if I do it numerically, I want to look at my skewness and kurtosis values. And because these the skewness and kurtosis values we computed already are Z transformed, I have a pretty good heuristic by which to judge whether something is within our tolerance of skewness and kurtosis. Remember, our data doesn't have to be perfectly normal for this assumption to be met. Our data just has to be not too abnormal, so to speak, for this assumption to hold. And it's also notable that we do have, sample sizes that are pretty accommodating here. But still, we should check up on this no matter what our sample sizes are. So I'm going to start with a numerically driven approach, and I already just did this approach when I created my factorial stats object above because I had skewness and kurtosis values. So I'm just going to look at factorial stats, and I'm going to tell it to reference the skewness and kurtosis variable. So if I print that, it'll just print those things out. Now the heuristic for telling whether the skewness and kurtosis values, whether they exceed what we would think of as acceptable ranges of abnormality, is to use the plus or minus 2 rule. And this heuristic changes from professor to professor or from statistician to statistician. Some people have different variations, some people don't. Some people have heuristics for the non-transformed way as well. But if you use the -2 to +2, because these are Z transformed, it basically, those are like a reference to where the critical values would be on like a Z test. Remember, the critical values for a two-sided or a two-tailed test is -1.96 and +1.96. So this is basically telling us, okay, if our kurtosis and our skewness are within 2 standard deviations of what we'd expect, or within 2 standard deviations of 0 because it's on a Z scale, then we're going to call that acceptable. And here we can see that, well, we have some kurtosis values that are over a standard deviation from perfectly normal kurtosis values. We're going to go ahead and just say that's within our tolerance there. So that's one way. It's also a good idea to look at this graphically, which we can do with ggplot. And you can do this using a density plot as well. Now, I didn't get to explain this because last week I didn't have kind of this access to screen recording software, and we just kind of distributed the ANOVA lab script. But there is a way to do this that actually helps us look at all the variables at once together. So here, I've just copied and pasted this ggplot code out of my key, and the first part up through geom density should look relatively familiar to things that we've been doing so far throughout the course. We have our dat object, we're specifying our aesthetic mapping or AES, and basically just saying, hey, put the dependent variable weight on the x-axis, break things up by diet, so create separate plots based on diet. And then this alpha just refers to the transparency of the density plot that we produce, whether it's like a solid color or whether it's a little bit transparent or opaque. And I tend to like things to be slightly opaque. And after we tell it that we want density plots here, we're adding this facet grid function to our kind of chain of ggplot code. And this is something I haven't explained before, but facet grid and other faceting family functions basically allow us to kind of subset our data into pieces and create multiple plots within one pane. So it kind of accomplishes the same thing as like a table function in that abstract kind of sense, where it's going to take whatever syntax I give it, instructions I give it on how to separate the data, and calculate different things for, calculate things specific to each subgroup. So here in facet grid, I've told it to create a series of plots where the rows are based on diet and the columns are based on exercise. So when I run this all together, I can see, again, like we just did, numerically, that everything works out with my skewness and kurtosis values, but I can see graphically that I now have this kind of matrix of plots where I have the no restriction diet, exercise yes or no, the vegan diet, exercise yes or no, and the veggie diet, exercise yes or no. And so when I visually inspect these distributions are not perfectly normal. However, they're normal enough for now. They'll do, and like we said, the values that we saw numerically are within their tolerance for me to feel comfortable that these distributions don't violate that normality assumption in any like real meaningful way, even though they're not perfectly normal. And again, we have sample sizes to help us out with the central limit theorem, although it's always a good idea to check on that first. Now we can turn to running the homogeneity of variance assumption checks. So I'm going to go ahead and create a code chunk here. And there's a few ways that we can do this. So there is the variance ratio method. To do that, we just want to take the variance ratio. Let me go ahead and label this first. Variance ratio, not ration, ratio. And we're going to take the max variance from all of our subgroups and divide it by the min variance in all of our subgroups. So the way I'm going to do this is, because I saved that summarize object as a the output of that summarize function as an object, I'm just going to reference the variances in that. So I'll go factorial stats $ to reference the var variable. In other words, to reference this column right here. So this is going to pull the max and the min out of this column. So I'll go max by min, and that'll give me my variance ratio. And I don't remember offhand what exactly the variance ratio should be, but I believe this is tolerable. And if I'm incorrect on that, someone please let me know. But I'm actually going to rely on a different type of way of checking my homogeneity of variance assumption, and that's for me to use a hypothesis test strategy, or a Levine test, which I'll just note as a hypothesis test. Now, a Levine's test is pretty easy to run because it uses the same type of syntax that you would use to actually run the ANOVA, and this is something that was in the last lab script as well for a one-way ANOVA. So basically, like we saw with t-tests and then ANOVA last week, we use this type of syntax when specifying what we would call a linear model, but you don't need to worry about that terminology just yet. So basically what you need to know is that we have the dependent variable on the left-hand side and our independent variables on the right-hand side of this tilde. Aside from that, we just tell it where to find our data, which is going to be dat, and we separate our independent variables by these asterisks. So here, this is basically saying, hey, we have the dependent variable of weight, and from weight, we have independent variables of diet and exercise within the DAT data set. So this is going to produce what's called the Levine's test. I'm also just going to add some quick code that I'm going to copy and paste from my key that shows us how to graphically do this. This is just like a very basic box plot, something even I think less complicated than the last question of assignment 1 when you were asked to describe what was going on. So I'll run all of these together, and what I'll find is I got my variance ratio that we talked about. Here's that 2.57 or thereabouts. And then here's the results of my Levine's test also. Now, what makes the Levine's test helpful to us is it has the null hypothesis that all of the variances across groups are equal to one another. So the idea is, if we have reason to reject that null hypothesis, that suggests that at least one of the variances is significantly different than at least one of the other variances. So the way to use this test is I look at my Levine's test, I see that my p-value is greater than 0.05, And that tells me that we have failed to reject the null hypothesis. Well, if the null hypothesis is that all of the variances are equal, and we then fail to reject that null hypothesis, that gives me some pretty strong footing to argue that the homogeneity of variance assumption has held up okay. Because if it didn't, we would expect to reject this null hypothesis and say that at least one of the variances is significantly different. So kind of like the normality thing we just looked at with skewness and kurtosis values, there is some tolerance such that our homogeneity of variance, our variances across groups don't have to be perfectly identical or homogeneous. But what we're saying here is they're not significantly heterogeneous or significantly different from one another. So we can proceed feeling pretty good about it. And you can also do this by looking at a box plot. And, these are, again, numeric hypothesis testing and graphical strategies I think are best used in tandem and not just done individually. But if you're just looking for a quick overview of your data, here's a good way to go about it. So I can see that broadly in kind of a subtle way that the non-exercise groups have a bit more variability to them. At least for the veggie, it's pretty pronounced. For the others, they're pretty close. I think there's just slightly more variability perhaps for no res, but it's, again, pretty close. It might just be the slight skew misleading me there. But I can see that by and large, these aren't too variable from one another in terms of their variances. It's a bit redundant to say. They're not too different from one another in terms of their variances. And I can also get a good view of normality here too. I can see that while there is some skew, in some cases the median is not perfectly centered in these boxes, suggesting the mean's getting pulled away somewhere. They look pretty normal to me. So going forward, I'm going to go ahead and assume that both my normality and my homogeneity assumptions are sufficiently met, and I can proceed to actually running the test now. So let's go ahead and try that out. I'm just going to take a quick moment to verify everything's going great with my recording. Everything's good. So let's go ahead and run our test. Just like we saw with the one-way ANOVA, we have this AOV function for analysis of variance that we could use to run our test. So I'm just going to call this two-way, since it's now a two-way ANOVA. I'm going to assign or save the results of this test to this two-way object. So analysis of variance, weight as a dependent variable, tilde, diet, asterisk, exercise. Spelled correctly. Exercise. Okay. And then finally, I got to tell it that we're operating on DAT as our data set. So this is going to run this two-way ANOVA test. From the cars package, we also have another function, this ANOVA function. So I'm going to delete these comments, pound signs, and I'm going to run this whole thing. So to walk through it, it's going to run the factorial analysis of variance and save it as an object two-way. And then we're going to use two-way in this broader ANOVA function, which just provides like a different style of output that is a little bit nicer to us than just the two-way on its own. So it's really just kind of like a formatting thing for our own benefit and convenience. And I'm going to save that as Factorial Anova. So if I look at this, I get my set of ANOVA tests here. And we run 3 different F tests when we do a Factorial Anova. We run a test for the interaction between the 2 independent variables, and then we run separate tests for each independent variable, which we refer to as the main effects. So if I interpret these, there's a specific order in which I want to interpret them. And it's first to check on the interaction. If there is a significant interaction, that is the most important part of running these tests to us, because it gives us the most nuanced or complex view of what's going on in our data here. It doesn't mean that the main effects aren't helpful or important, but the interaction is kind of like where the money is when you're running a Factorial Anova. The whole point of running a Factorial Anova in some ways, or really in most ways, is to determine if there's an interaction in the first place. So for example, we know that the 3 diet types lead to significant differences from our one-way ANOVA situation, or just because I know that to be the case here because I made the data. But now I want to know, does exercise actually moderate that relationship? So does that relationship between those three dietary types in terms of weight change if we also consider exercise as a factor? So here, our diet exercise line, this is our interaction, and we can see that this is very, very significant. So this is kind of like our first thing to interpret and would be considered like the main finding of this analysis. And what this is telling me is, yes, in fact, exercise does moderate the relationship between diet and weight. In other words, the relationship between diet and weight changes depending on whether someone exercises or not. And I'll show you what that means visually in just a second, which might be a little bit more explanatory. But further, after we interpret and then report that interaction, we can go and turn to these main effects. So these basically tell us whether there are significant differences with each independent variable on their own. So for exercise here, we have a significant main effect, which means that all else being, held equal, people who exercise have a significantly different average weight than people who don't exercise. It's effectively like running a t-test because exercise only has two groups. So here, if you exercise, you have a significantly different weight than if you don't exercise on average, broadly speaking. The same can be said for diet. We have a main effect of diet, which tells us that of the three groups in the diet variable, no res, vegan, and vegetarian, at least one of those groups significantly differs from at least one other of those groups, independent of considerations regarding exercise or the interactions or anything like that. So, the interaction, again, is what's most important to us. But here we can see that if we were to, just run one-way ANOVAs on each of these independent variables separately, that those one-way ANOVAs would come back significant as well. So next, let's look at the visualizations of the interaction. And I've gone ahead and left this in your slide just because I don't expect you to code out all of this ggplot. And I've also included some scplot code here, which is what Dr. Siegel likes to use in lecture. And then finally, even though it's not a visualization, I've included the cell means here just so we can get a look at those. So basically all I've done is select out diet, exercise, and mean. And let's see if this runs. It might throw me an error now that I think about it, but let's check. Okay, all good. Sometimes when you use the PSYC package, the select function likes to act up. So here, I've got diet and exercise, and I can just look at my group means, or these are referred to as the cell means sometimes because when we put them into a table, it's a mean per cell. A lot of times you'll also see this as a crosstabs, which is what I think, that's my Carfax statement, don't look at that. Crosstabs, which Dr. Siegel puts in lecture. So a lot of times you'll see them reflected with the levels of the independent variables as kind of like the row and column headings, and then the means in there as individual cells, which is why we refer to them as the cell means. So here I've just provided a table with means as a column, so it's not exactly the same as a crosstabs, but we can still refer to these as cell means, and I hope that kind of gives you an indication of why we call it that. Really, when we run a Factorial Anova, we're after a plot like this, and I would suggest always including this type of plot whenever you conduct a Factorial Anova and report it anywhere, because it's almost guaranteed to be expected by readers of a research article when they come across a Factorial Anova. So what this plot has is 6 dots, and each of these dots represents one of those cell means. I have 2 lines here. The top line in this kind of like salmon color is for exercise no, so people who didn't exercise. And in this kind of like neon tealish color, this is exercise yes. On the x-axis, I have the levels of the diet independent variable, so no res, vegan, and veggie. And then on the y-axis, I have my dependent variable, which is weight, and that's again a continuous variable. So here I can see that the no-res group that did exercise had a lower weight than the no-res group that did not exercise. And the same goes for the vegan group. Those that exercised as vegans had a slightly lower weight than those that did not exercise as vegans. However, for the vegetarians, those that exercised have a little bit more weight than those that did not exercise. Now, I don't have a rational explanation as to why that would be the case, other than I made up this data and I wanted there to be an interaction. So if you're a vegetarian that exercises, please don't get offended. But you can see that if you take a look at this and kind of break it down for a minute, you can really see what we mean by an interaction between exercise and diet. Or put another way, you can see how the effects of diet change over levels of that variable depending on whether people exercise or not. For example, if you have a no restriction diet, you don't really watch what you eat or adhere to any dietary restrictions. You just kind of eat what life throws at you. You can see that exercise has a much larger effect on your overall weight than if you were a vegan or a vegetarian. So you could argue that maybe vegans and vegetarians eat a little bit healthier. So if they do not exercise, the negative effects of that, for vegans, for example, is less dramatic than the negative effects of not exercising if you have a no restriction diet. So in that way, exercise moderates weight across levels of the diet independent variable. So it's more important to exercise. Based on this data, at least, we have evidence to suggest it's more important to exercise if you have a no restriction diet than if you have a vegan diet. So that's one thing. That's our significant interaction and how we'd interpret that. Does the DV change across a level of one independent variable because of differences in the other independent variable, and so on? So another thing we could look at are these main effects. The main effects, again, tell us whether one variable on its own is significantly different across its own levels. Basically, it's like running a one-way ANOVA just with that independent variable. So if our sample sizes are the same, we kind of have a methodology to interpret this in a straightforward way. I can just kind of look at the halfway point between each level of exercise and assume that that would be what my independent variable for diet means, my group means for just the levels of diet, independent of the exercise variable. So in other words, if I were to pretend this exercise variable wasn't here, I can kind of imagine a line where there's a mean for no res here, a mean for vegan here, and a mean for veggie here, in between those 2 points that exercise bifurcates there. And so if I look at that, I can kind of envision some significant differences between no-res, vegan, and veggie. For example, I could imagine that there'd be a significant difference between having a mean here and having a mean way down here. That's a pretty sharp, drastic drop there. And there could even be a significant difference between vegan and veggie. So that main effect for diet does seem pretty sensible to me. We can kind of do the same thing thinking about exercise and how that main effect might occur if the diet independent variable was not present. So if I were to imagine that these 3 dots could summarize into just being 1, I'd imagine that there'd probably be a mean for exercise yes, somewhere, I don't know, like around here, like maybe 170 or so. And if there was going to be a mean weight for exercise equals no, then that would be probably around here, like 180-ish. So if I imagine kind of like the average of the blue line dots and the average of the red line dots, like the red line would probably be here for no, the blue line somewhere down here, I can see how those might be significantly different too. Now, there is no science to this, at least without the inclusion of error bars. There's no science to this, so it really is kind of just like a quick judgment call, and by no means should you expect to be super accurate when interpreting these interactions visually. You should always go back and look what the actual F values are and what the P values are, and look at things like confidence intervals and so on. So in other words, you should always go back and look at the actual hypothesis test to confirm. But this can give you a pretty quick idea of the relationship between these two independent variables and how that relationship affects weight on average among your sample. So here's the same plot that includes error bars. This is the plot generated by scplot. It's really cool that this includes error bars in it, and you don't have to go through the hassle of coding those out in ggplot. However, I do prefer ggplot. I just think it's like a cleaner plot, and it's just kind of my preference because I use R a lot. I know this is a plot generated in R too, but it kind of looks like more of a, I don't know, something like an engineer would produce. It's just a little dull to me, and that's not that's not a pointed statement about Dr. Siegel's use of it. In a lot of ways, it's kind of advantageous to have these dull plots because it's just the data that you're seeing. It doesn't distract you in any ways. Plus, these error bars are really helpful. I can already tell that these things are significant across each level because these error bars have no overlap whatsoever. And while I'm not going to get into like the visual interpretation of the error bars specifically, that's actually a pretty solid heuristic that you can use in the future. If the error bars don't overlap in any way, you can kind of assume that they're significantly different. So for example, the error bars between diet yes and diet no for vegetarians don't overlap. I'm going to go ahead and make a pretty good guess that if I were to isolate the vegetarian participants, they'd have a significant difference in weight if I did a t-test on exercise. And I can do that across diet as well. So here I know that the no res and the vegan group that do not exercise, those error bars don't overlap either. So I'm pretty confident if I were to isolate the people that don't exercise and run a t-test between no res and vegan, that there'd be a significant difference there as well. So that's the end of part one. So I guess to wrap up, we'll just say a couple things to kind of review. First, whenever we are doing a factorial ANOVA, by definition, we're doing a little bit more than we would with what we call the one-way or simple ANOVA, which only uses one independent variable. When we conduct a factorial ANOVA, we're going to be using two or more independent variables. Now, it's not a good idea to just like add independent variables willy-nilly, and if you have a whole bunch of them, it might be a better idea to do a different kind of analysis because it gets really hard to interpret interactions beyond two or three variables, independent variables. But it is possible to conduct those types of ANOVAs if you want. So that's the first thing. Our factorial ANOVA is going to be different from a one-way ANOVA because it just contains more independent variables. And in this case, we called this a 3x2 factorial ANOVA because there were three levels of diet, no res, vegan, and veggie, and two levels of exercise. Let me make sure I said that correctly. There are three levels of diet, there are two levels of exercise, hence 3x2 factorial ANOVA. Third, the interaction is the most important thing in a factorial ANOVA. So even though you might have multiple significant tests for interaction and main effects, always start by interpreting the interaction and make that the focal point of your results regarding this analysis. Reporting the main effects is important and helpful too, because it does kind of give you a better idea of like the data pattern and kind of explains the interaction in a little bit more detail. But the fact that there is an interaction is the really important finding here, because it tells you that that one variable you had alone, like diet, is moderated by another variable. In other words, another variable changes the relationship between diet and weight, and in this case that was exercise. So that's the end of part one. Again, if you have any emails about any of this, or excuse me, if you have any questions about any of this stuff, please just send me a quick email. And I'll remind you once more that this is more meant to be kind of like a practical guide to Factorial Anova. We're going to save any types of major conceptual review of factorial designs for Psych 410, which is something I actually strongly advise you take, whether you are, trying to be like a data-oriented person or not. The professor who teaches it is a pretty brilliant dude named Mike Moran, and your knowledge of statistics will grow so much deeper taking a class with him. And ANOVA is probably the most, or tied for the most common type of analysis you'll find in general psychology. So it'd be good to have a pretty familiar knowledge with that. It might be tied with like regression, for example. Okay, so part 2. Here we're just going to practice interpreting interactions visually. And as I said when we were going through the interaction for that two-way ANOVA just a second ago, that factorial ANOVA, there is no science to doing this visually. There is not necessarily a perfect way to determine that there's a significant main effect or not. It's kind of just more of a heuristic. If I see this, I kind of like feel like it might be a good main effect or not. It's always something that you should confirm in the actual F test before you make any strong claims about it. So for example, if I'm just skimming a research article about something, and I maybe I'm quickly reading it, or I'm reading like the discussion without reading the results necessarily, or something like that, I might look at these types of visualizations to make a quick judgment about something. But if I'm going to go ahead and use that article in like a literature review of my own writing, I'm going to make sure I know for a fact that there's a significant main effect before I go and claim there's one. So just be mindful of stuff like that. This is kind of more of a quick interpretation, like all visualizations are. So the instructions for this part of the lab script are to run the following code chunks one at a time, which I've left in and provided here for you, and answer these two questions. Is it plausible that there's a significant interaction? Or, and is it plausible that there are any significant main effects for these two factors? And if so, what are they? So the code in each of these things is pretty simple. I've created two factors earlier at the very beginning of the script. And here I'm just creating basically a dependent variable, a y-axis. And then I'm just plotting those things together and making these same types of interaction plots here. Now, I'm not doing this from raw data. I'm just like basically saying here are the means for all of these factors, just for the purposes of creating the visualization. So this is kind of less about the code and more about just visual interpretations that of the plots the code creates. So I'll run this first one, and this is what I get. So my question here is, 1, is there a plausible reason to suspect that there's an interaction? And here's how I would answer this. I would say that most likely there's no interaction. And the way that we can tell whether there's an interaction or not is basically by looking at whether these two lines, or these two lines, whether they cross or they look like they're gonna cross if I were to like extend them hypothetically within like a reasonable distance of the levels that I have. So for example, yes, it's true that this is smaller of a difference than say something up here, and that, ad infinitum, if these were to keep going, they'd eventually cross. But by and large, these lines mostly look parallel. They're close to being parallel. So I'm going to assume that there's probably not an interaction here. Again, some Carfax for you. I really should have closed that out. You can look at a slide Dr. Siegel has here on interactions and get a good idea of this. Basically, the idea is if the two lines change together in a similar way, that there's no interaction. And that is in really good keeping and good fitting with the way that we kind of defined verbally what an interaction was, right? We said that an interaction is when the relationship between some independent variable and the dependent variable changes due to a second independent variable kind of moderating those things. So for example, we said that the relationship between diet and weight changes when we consider diet. And that change is going to be reflected by some sort of cross or intersection between these two lines at some point in this interaction plot or somewhere thereabouts. So if the lines look by and large the same, yeah, that might suggest a main effect, but that a possible main effect, but it does not suggest an interaction, because here we can see that while there's differences between levels of factor 2 here, the two different colored lines, that difference is pretty much equal across levels of factor 1. And so there's no interaction, there's no real like moderating effect here that we would expect from a significant interaction. So there's no interaction here. I'm also going to say that there's possible main effects for both, and it's more likely for factor 1. And again, this is mostly like a hunch-oriented practice. I don't know for sure without looking at the test, but I can see here that the gap between these two lines is pretty large overall, and if I use my trick of just trying to kind of ignore the presence of one factor and focus on the presence of another, I can kind of start to see this. For example, if I imagine that factor 2 doesn't exist and these two separate lines should really just be one line, I can imagine that there's a mean here, a mean here, a mean here, and a mean here. Again, 1, 2, 3, and 4. And I could kind of imagine that this mean might be significantly different than this third mean here, which would lead to a significant main effect. Likewise, if I were to imagine that factor 1 didn't exist and that I only had two group means for each level of factor 2, there'd probably be a mean for the first level, or the salmon line, somewhere around here, and a mean for the second level, or the teal line, somewhere around here. So this might be a significant difference also, although this difference seems a little bit more drastic across levels of factor 1. So that would be my first interpretation. So let's just keep going. I think I've got maybe 4 or 5 of these to get through. Looks like quite a bit. Looks like 8. So let's just kind of power through them then. So looking at the second one. All right. So here it's really apparent that I have an interaction because my two lines intersect. And it's just really obvious if you kind of, again, place yourself in the mindset of evaluating, does the relationship between factor 1 and the dependent variable y change differently over because of levels of factor 2? So here I can see, for example, that the difference between the levels of factor 2 in the first level of factor 1 are a lot smaller than the differences from the levels of factor 2 in the fourth level of factor 1. So there is most definitely an interaction here. In all caps, interaction! Exclamation point. So we've definitely got an interaction here. I'm going to say that there's also a pretty likely main effect for factor 2. And that's because if I were to pretend factor 1 doesn't exist, the means for the levels of factor 2 would be somewhere around here for level 1, and probably somewhere around here for level 2. So that's like, here to here. That's a pretty large gap, so there might be a main effect there. And then I'm going to say, in reference to factor 1, that there's probably no main effect for factor 1. And that's because if I kind of split the difference between the lines here, there'd be, and forget that factor 2 exists. If I were to, in other words, kind of collapse the difference between these 2 points, I'd have a mean here, a mean here, a mean here, a mean here. In other words, I'd have a line that kind of looks like this, with just like a slight dip on the first level of factor 1. And so it's pretty likely that there's not a main effect there. So yes, factor 2 does have a really influential role on weight across levels of factor 1. It is definitely an interaction. However, if I were to remove factor 2, it's, you know, it might be possible, but it seems, at least by this visual inspection, that there's probably not going to be a significant f-test if I were to just do a one-way ANOVA for factor 1. And I'll also say, I've made reference to this several times already, but I'm using this language like pretty likely and probably very much intentionally, because again, you need to look at the actual f-tests for these things to confirm, and these are just like hypothetical graphs. So don't be super firm on your visual interpretation, but use it as kind of like a quick heuristic or guide. So let's just keep going. Here's interaction 3. And so here, I do not have an interaction, and it's incredibly clear to me because these lines are perfectly parallel. So no interaction at all. And it's very much true that that is the case. It's not really a question in the slightest. So there's no interaction at all here. So I'll turn to looking at the main effects. If I were to imagine that factor 2 did not exist and just take the average of each of these levels of factor 1, I'd have a line that looks like this: mean, 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 mean. So it'd be a straight line kind of through the middle here. So I am super confident that there is no main effect for factor 1. Very confident, in fact. I'll just go ahead and say no main effect for factor 1 without couching my language behind like probably or pretty likely or something. For factor 2, if I were to imagine that these 4 dots collapsed horizontally into just one mean, so the mean for level 2 on factor 2 and the mean for level 1 on factor 2, I could see where this gap here would be large enough to have a significant main effect. And again, I don't know for sure, and there are definitely other factors that play into this, so it's very much like an estimate. So I'll just say possible main effect for factor 2. I could at least see, though, that they are different. Maybe not significantly so, but probably. Going down to my 4th interaction here. Let me run this. Okay, so here, there is definitely an interaction as well. Definitely an interaction. And I can tell because at 2 points, these lines are very close to crossing. But again, if I use my just my kind of verbal idea of what an interaction is, do the differences on one factor change significantly over levels of another factor, or you can replace factor with independent variable if you want. I can see here that the differences between levels of factor 2 at the first level of factor 1 are pretty small, but the differences between levels of factor 2 on the second and third level of factor 1 are quite large. So this is kind of like a moderating effect of factor 2 on the relationship between factor 1 and the dependent variable. So here, there's definitely an interaction. Now, if I look at factor 1 and I imagine that factor 2 doesn't exist, I might want to ask myself whether there's a main effect or not. Well, if I look at the middle of each of these dots, like we have been doing, I would get a line that looks something like this if factor 2 didn't exist. There'd be a mean here, a mean here, a mean here, and a mean here. So it would look maybe like that. That's not a very large difference between those means there. And while, yeah, it might be possible that there's a main effect, I would lean towards saying that it's unlikely. Excuse me, let me reset my cursor here. That it's unlikely there is a main effect for factor 1. If I do the same thing for factor 2, again, I'm going to pretend that levels of factor 1 are irrelevant, or kind of take the average of each line independent. I don't know, there'd be like maybe a mean here for the second level of factor 2, and maybe a mean here for the second level of factor 1. and that seems like a pretty large gap. So I'm going to say that there's likely a main effect for factor 2. So I'll just keep plugging away here. For the fifth interaction plot, we get this line, and this one's a little bit trickier because there are some bends that are not in step with each level across factor 2 here. So they differ in their overall shape per line, whereas so far we've seen things that are kind of in lockstep like this, right? So if I look here, I'm going to say that these lines, although if they were to keep going in this trajectory, would have like kind of a chance to intersect, the gaps between factor 2's levels don't really change a whole lot over levels of factor 1. They are different. This is a smaller gap than this, for example. But I don't know that it's large enough to cause a significant interaction. So I'm going to say unlikely there is an interaction. As far as the main effect for factor 1, if again I take the middle of these dots, I get a line that looks like this. So it would be some kind of like slightly crooked line. But I don't know if that would necessarily be significant. So I'm also going to say that there's an unlikely, that it is unlikely there is a main effect for factor 1. And then if I look at factor 2 and I pretend that factor 1 doesn't exist and I just take the average of each of the line's 4 means, there'd be a group mean for level 2 of factor 2 about here and a group mean for level 1 of factor 2 about there. That's a pretty large gap. So I'm going to go ahead and say that there's probably a main effect for factor 2. Continuing on, we just got 3 more of these to go, so bear with me. If I look at the 6th interaction plot, I run this. That is the most obvious interaction I've ever seen. So we're definitely going to say interaction with some emphasis here. Definitely, most definitely an interaction. If I look at the main effects though, there doesn't seem to be any. So for example, if I took the average of the 4 teal dots and then the average of the 4 pinkish salmon dots, those averages would fall pretty much in the same spot, right? Like it'd be right in the middle. So there's very low chance, very unlikely a main effect for factor 2. For factor 1, if I instead took the average between each level of factor 1's dot, and again that's for trying to ignore factor 2, I would have something here, I'd have something here, here, and here, and that would just be kind of a straight line. There wouldn't really be a difference across levels of factor 1. So I'm going to say unlikely a main effect for factor 1 as well. All right, here's our second to last interaction plot. I'm going to go ahead and run this, and I get something like this. This one is pretty easy for me to interpret in terms of the interaction. There's also there is no interaction here, I should say, and that's because my lines don't cross and they remain pretty much parallel, even though they dip a little bit at level 2 for factor 1. There's no real moderating influence of factor 2. In other words, these things do not change across levels of factor 1, the levels of factor 2 that is. So there's no interaction. We might have a main effect for factor 2, for factor 1. If I were to split the difference between each level of factor 1, that would be something like that, that, and that. That difference might be significant. Again, I don't know for sure, but it looks like it probably would be. So I'll say possible main effect for factor, that should just say 1. And as far as factor 2 is concerned, that one's a little bit tougher. So if I were to take the average of the 3 blue group means, that'd be, I don't know, be something around here. And the average of the 3 salmon group means that'd be something around here. So I'm going to be really careful, and I'm going to say that this may be a main effect for factor 2. This one's definitely a lot more ambiguous than some of the other ones we've seen. And finally, our last interaction plot of the lab script. I'll go ahead and run this. And this one's a little bit trickier because we can definitely see a difference in how the levels of factor 2, we can definitely see difference across the levels of factor 2 depending on the level of factor 1 we're looking at. So for example, this gap is smaller than this gap probably by half. It looks pretty small. So here I would actually, though the lines do not cross, I would say that this difference is large enough for me to be pretty confident that there's an interaction. And if we look at the lecture slides from lecture 9, we can see here that this is something we might expect. Now the lines again don't cross, but we can see that there's a pretty decent difference in the gap between levels of factor, the first level of factor 1 and the third level of factor 1. So here I would say that there's likely an interaction. Even very likely that there's an interaction. For the main effects, if I look at these and start to split the difference, I would say that there's probably a main effect for factor 2. For example, if I took the average of the 3 salmon means, and that would be about here, and the average of the 3 teal means, that would be about here. That's a pretty sizable gap, right? So I could see that that is likely a main effect, I think. For factor 1, it's a little bit trickier. If I split the difference here, I'd have a group mean there, a group mean there, and a group mean there, and that just doesn't really look like a huge difference from 1 to 3 even. So I'm going to say that it's unlikely there is a main effect for factor 1. So we've seen a bunch of different possible interactions on these plots. Some of them are very obvious to interpret whether there's an interaction or not. Remember, our go-to sign is whether the lines cross or whether they look like they should or will cross, or frankly, whether the gap between the two lines is really large in some places compared to others. So this is a great example. The gap's pretty small on level 1 of factor 1, but pretty big on level 2 of factor 1. So that's the gist of Factorial Anova. And again, this is meant to be more of a practical guide, not so much a conceptual review this time. I've already kind of reviewed the testing side of things, and I guess I just gave a small review of the plotting side of things. Just remember that when we're talking about Factorial Anova, we're trying to see the influence of levels of one factor independent variable and how those change the relationship between the other independent variable and the dependent variable. So again, how does whether one exercise or not change the relationship between diet and weight? Does exercise moderate weight across different levels of diet, and so on? So I hope this format has been helpful. It's definitely new to me to try something like this. I hope this is an adequate substitute to doing this live, or perhaps maybe it's even a better presentation. I don't know. At either way, at either rate, I hope all of you have a good rest of your week, and as always, I hope all of you are doing well, all of you are healthy, and I'll say it one last time. I said this in the Anova review. I really hope that all of you guys are being attentive to your mental health over this time as well. And, I totally sympathize with the idea that being self-isolated and remaining socially distant from people is challenging, and it's tough, especially when the stresses of the end of the semester and writing papers and stuff like that are bearing down upon you. So try to stay well as best you can. And if you need anything, please don't hesitate to email me and potentially set up some sort of like Skype office hours, or get whatever help that I can realistically offer you in the position that we're in. So I hope you guys have a great rest of your week, and I'll be uploading more stuff as the course proceeds. So take care. Bye.